Hi, my name is Alex Lopez, and this is my lab report for Physics 2211 Lab 1. The purpose of this lab is to apply Isaac Newton's second law of motion to analyze the motion of an object moving with a constant velocity. And this was done by rolling an object, I used a marker, across a flat surface and analyzing its motion using an application called Tracker, which allows you to see exactly how far the object traveled and how long it took. And then these data points were then graphed alongside a computational model of the velocity, which was coded in Python using GlowScript. To define Newton's second law, it describes the relationship between the force on an object, the object's mass, and its acceleration. And it can be expressed a couple different ways. The first is just by saying that the net force is equal to the mass of the object times its acceleration. And that can be rewritten as saying the mass times the change of velocity over time, which from there you get that the net force is equal to the change in momentum over time. And then from there we can derive the formula for the velocity update, which is the final velocity is equal to the initial velocity plus the net force over the mass times the change in time. But in this experiment, we are assuming that the net force is 0, so there's no change in velocity. So the final velocity is just going to be equal to the initial velocity. And then we also have the position update formula, which is that the final position is equal to the initial position plus the average velocity times time. So here's the tracker video of the marker rolling across the floor with its position being tracked frame by frame. And so you can see it has a pretty constant velocity in the x direction, in the negative x direction. So I made this GlowScript code using the data from the tracker video. So first the position is set to 979, which was the initial position of the marker in the video in millimeters. And then the velocity is negative 570, which is the average velocity of the marker in millimeters per second. And then we have t equal to 0 for the initial time, and delta t, which is 0.033, because the video was filmed in 30 frames per second. And then we have a while loop, which is while t is less than 2.89, which was the final time. And so we have the velocity vector is going to stay the same, but the position is going to be equal to position plus velocity times delta t, which you'll notice is straight from the equation I showed earlier, where final position is equal to initial position plus average velocity times time. Here we have the results. So the blue line shows the observed position over time, and the orange line shows the predicted position over time, which is from the computational model from the code that I just showed. So you'll see that the observed position is not quite in line with the predicted position, and that's because we didn't account for friction. So in reality, the marker slowed down a bit over time because of friction, and the predicted position is just a constant velocity, which was the average over the whole time period. And finally, we have some conclusion questions. So first, what if you were to flip the axes if positive x and negative x were interchanged? So since the marker was rolling to the left in the video, it was moving in the negative x direction, which led to the graph having a negative slope. So if the positive x and negative x were interchanged, my graph would have had a positive slope, but still the same magnitude. And then for the second question, it is not possible to determine exactly how many pushes and pulls were added together to give 0 net force because we examine the system as a whole, and the system in this case is just a marker, but we didn't look at individual forces acting on it. So we just know that the net force is 0, which is why the velocity stays constant.